All right, so I want to take a bit of time and talk about some fairly straightforward calculations that deal with percent composition and also empirical formula. So I want to go right to the source um, with the infamous Dr. Collins and see if we can break down some of the solutions in these exercise problems. So one thing that I guess it would be a good idea for us to review, or just to review calculating formula weights for different types of ionic salts. So let's look at 7.2, where we calculate the formula unit, the formula weight for ammonium carbonate. And what I'd like to introduce are some thoughts of how we can make these calculations as easy as possible. So if we consider ammonium carbonate, we have NH4 parentheses subscript 2 CO3. Now, we know that nitrogen has a molar mass of 14, and each hydrogen has a molar mass of 4. So each NH4 is going to have a mass of 18. And we have two of those, so both of our ammonium ions gives us a mass of 36. Each carbon is 12, 3 oxygens is 48, so a carbonate will be 60. And when I add these together, I will get a formula weight of 96. So this will be 96 AMUs as a possible unit, 96 grams per mole is a possible unit. If we look at our second example, we have sodium sulfate decahydrate. Again, if we start thinking about functional groups or polyatomic ions and their charges and their masses rather than the individual atoms, these become a lot easier to handle. So, for example, sulfate has a mass of 96. Sulfur is 32. Each oxygen is 16. 16 times 4 is 64. 64 plus 32 is 96. Each sodium is 23, so 2 times 23 will be 46. 96 and 46 adds up to 142. And if you do enough of these problems, you really should be able to memorize enough of these patterns where doing these problems becomes a bit less cumbersome. So when I have Na2SO4 decahydrate, I know water has a mass of 18, 16 plus 1 plus 1. And when I multiply that by 10, that piece becomes 180. This piece becomes 46. The sulfate becomes 96. Together, this is 142. When I add everything together, I'm going to get a mass of 322 grams per mole, or 322 atomic mass units. So those are fairly easy computations that you might see on your PCAT. Now let's look at doing a simple gram to mole conversion, or doing a mole to gram conversion, and we'll use the formula weight as an essential conversion factor. So 60 grams of NaOH contains how many moles? We start with what we know. We have 60 grams of NaOH. we know from previous videos that the molar mass of NaOH is 40 grams per mole. So there are 40 grams of NaOH in 1 mole of NaOH. Of course, 60 divided by 40 is simply 1.5. So I have 1.5 moles of sodium hydroxide. Looking at the second problem, what's the mass of 2 moles of sodium sulfate? This problem is significantly easier now that we've already determined that the mass of sodium sulfate is 142. We have 142 grams per mole, and we're going to multiply that by 2 moles. That becomes 284 grams of Na2SO4. Okay, so let's go back to the next set of questions. Let's look, in doing a percent composition problem, for instance, when we have the percent composition of NaCl, what makes this problem interesting is you need to be able to estimate the mathematics. So if we look at NaCl, we know, and probably since they don't give us the periodic table in this exam, they're going to give us structural information or mathematical information about the molar masses. So sodium is 23, chlorine is 35.453. So if I'm trying to find the percent, what I'd like for you to see is that this number 35 is really, really close to 23 plus half of 23. So just hear me out on this. 23 plus 11.5 is 34.5. Meaning that when I have the mass of Cl, so when I look at 23 over the total mass, that is 58.453. It is 23 over 23 times 1.5. The 23's cancel. This is 1 over 1.5. I can multiply the top and the bottom by 2. In other words, if I multiply a number by 1, I don't change its value. This becomes 2 over 3. Now, what we're ignoring is that there's another Cl that's waiting here for us. So really what this is 23 plus 23, which is from the Na, plus 23 plus 23 over 2, which is the mass of Cl. That's the estimating that I'm doing. And so when I do this, I have 23 over 46, which becomes 1/2. I have 1 over 2 plus I have 23 divided by 2. So I realize these numbers become cumbersome after a while. So let me get a whole new easel and go back and show you this step by step. So I have 23 over 23 plus 23 plus 23 over 2. Let's factor out a 23 on the bottom. And this will be 1 plus 1 plus 1/2. In other words, the two 23s now cancel. And I get 1 over 2.5. If I multiply the top and the bottom by 2, I haven't changed the value, it's now 2 over 5. This is the percent composition of Na+. This is 40%. I've done some estimating. We're going to look at the actual answer in just a moment. And I want you to evaluate what I've done estimating and the math that results from estimating with regards having to do long division on your test, which you never want to do. This means that the CL has to be 3 over 5 or 60%. So this should be 60% CL, 40% Na. Let's see how close we were. 39.3%, 60.7%. We were very close. And in the context of a multiple choice exam question, this is one that we can easily eliminate the 3 distracting answers and pick the answer that will get us credit for that particular question. I'd like to do one last calculation for this particular video, and that is the empirical formula. We have a compound that is 27.3% carbon and 72.7% oxygen. In other words, all we have is a molecule with carbon and oxygen. Now, there's a couple things that as a chemist I would think about early and often. And one is, what kinds of compounds do I know that exist in nature that have only carbon and oxygen? And honestly, I can think of only 2. One would be CO and one would be CO2. Now we know that the percent of carbon in this problem is 27.3. And the percent of oxygen is 72.7. So I'm going to use as my basis CO and CO2. Now what you could do on this problem is you could look at the answer choices and do some quick calculations. That would be a really nice strategy. So I have carbon is 12, while oxygen is 16. So 12 over 28. How close is that to 27.3% versus 12 over 44? Now 27.3% is 27.3 over 100. If I look at this particular fraction, I can multiply it by 2 over 2, and I would get 24 over 56. These numerators are very close together, but the denominators are off by a factor of almost 2. So that's not a good answer choice. So we're going to discard CO. Let's try CO2 now, because CO2 would be 24 over 88. Now look at this. The numerators are close. The denominators are close. This is the answer that I would pick without doing any further mathematical calculations. You could reduce this if you wish to 6 over 22, to 3 over 11. And the beautiful thing about 11 in the denominator is I'm going to take the numerator and multiply it by 0.090909. Notice if I multiply this by 3, what do I get? 0.272727. In other words, I get the 27.3%. So by two different ways, we're able to surmise that CO2 is the best answer choice without making this a brain-busting mathematical problem. And I think that's really important with these types of problems that you see on a PCAT or on a DAT. Remember, the questions are very similar in nature. So whether you're approaching this for the dental school admissions exam or for the pharmacy college admissions exam, this technique works well on both exam types. Let's do a couple of extra problems with these empirical formulas. So again, if we go to El Doctor Collins on example 7.7, we have a compound that's 80% carbon and 20% hydrogen by mass. It has a molecular weight of 30 grams per mole. Determine the molecular formula of this compound. Now, I'm going to approach this differently as an organic chemist, so just please bear with me. I could have a molecule with carbon and hydrogen and have C2H4. I could have two carbons and have C2H6. By the way, this has a mass of 16, while this has a mass of 30. This is exactly what I'm looking for. So I'm going to suspect that we have ethane as our answer. Now the question is 24 over 30. 24 is the mass of two carbons. 30 is the mass of the entire ethane molecule. When I break this down, that is when I divide the top and bottom by 3, I get 8 over 10, which is precisely 80%. And without considering hydrogen, I know that 6 over 30 breaks down, again, when I divide top and bottom by 3 into 2 over 10. This is also going to be the expected 20%. So I know that the molecular formula of my compound in this question is C2H6, and I am done, and I can move on to the next problem. You don't want to consider 100 grams, say you have 80 grams of carbon, convert that to moles, divide by the lowest number of moles if you don't have to do that. So if you're clever, this really pays off well because you can do this problem in 30 seconds and know that you have the right answer. So let's do one final problem for the evening, and I'm going to do problem 7.8. I have a sample of a compound. I have 0.9 grams of element A, and the molar mass of A is 60 grams per mole. That's 0.9 over 60 moles. Now we could do a lot to break this down if we wish to. We could say this is 9 over 600. We could say, we could divide top and bottom by 3. We could say this is 3 over 200 moles. We could convert that to a decimal. It's half of 0.03, so it's 0.015 moles of A. And then we're going to do something similar for B. I have 0.6 grams of B, and the molar mass of B is 40 grams per mole. So this is going to be 0.6 over 40, which is 6 over 400, which is 1.5 over 100. Notice I have 0.015 moles of B. I have the same number of moles of A that combine with the same number of moles of B. Therefore, the empirical formula must be 1 atom of A combines with 1 atom of B. I have AB. Again, a different way of approaching the problem that makes the math easier. Do not attempt to simplify these with long division. Play with fractions until you can do a reasonable approximation, and you'll find the math cleans up almost every single time for you. So I'm going to end this video, and we'll pick up some more problems with percent composition and empirical formula. So until then,